How does resonance impact different AC circuit configurations? Imagine tuning a radio to just the right station, and suddenly everything sounds crystal clear. That's resonance at work, but in electrical circuits instead of radios. When you understand how resonance affects different AC circuits, you can see how engineers design devices for filtering signals or tuning frequencies. In a series RLC circuit, which has a resistor, inductor, and capacitor connected one after the other, resonance happens at a specific frequency called the resonant frequency. This frequency is calculated by dividing 1 by 2 times pi times the square root of the inductance times the capacitance. When the circuit hits this frequency, the inductive reactance and capacitive reactance are equal but opposite, canceling each other out. As a result, the total impedance becomes just the resistance, which is usually much lower than at other frequencies. This means the current in the circuit reaches its highest point at resonance. The voltage across the inductor and capacitor can become very high because energy keeps bouncing back and forth between them. The sharpness of this peak depends on the quality factor, which tells us how selective the circuit is. A high quality factor means a narrow, sharp peak, perfect for tuning into specific radio stations. If resistance increases, the peak becomes broader and less pronounced, making the circuit less selective. Now, in a parallel RLC circuit, where the resistor, inductor, and capacitor are connected in parallel, resonance behaves differently. At the resonant frequency, the circuit's impedance reaches its maximum. This is because the inductor and capacitor exchange energy, creating currents that oppose each other. These currents cancel out, so the overall current from the source drops. This makes the circuit act like a high impedance barrier at that frequency, blocking signals. It's often used as a filter to block unwanted frequencies while passing others. The quality factor here is inversely related to the series circuits, meaning a higher quality factor results in a sharper impedance peak. Resistance in the parallel circuit dampens the resonance, preventing it from becoming too sharp or unstable, which helps keep the circuit stable and predictable. In practical terms, engineers use these resonance effects to select specific frequencies, filter signals, or create oscillators. Series resonance circuits are great when you want maximum current at a particular frequency, like in radio tuners or audio equipment. Parallel resonance circuits are useful when you need high impedance at a certain frequency, such as in filters or frequency-selective networks. Resonance impacts AC circuits by changing how impedance and current behave at specific frequencies. In series circuits, it minimizes impedance and boosts current flow. In parallel circuits, it maximizes impedance and reduces current. Resistance influences these effects by controlling how sharp or broad the resonance is, making circuits more stable or more selective. Knowing how resonance works helps electrical engineers design better communication systems, filters, and power electronics. It's a key part of understanding how AC circuits respond to different frequencies and how to control that response effectively.